Hi, my name is Joseph Belangi, and today I'll be presenting alongside with Darren Tang. We'll be talking about the solutions to corrosions in nuclear reactors. Here are some of the topics we'll be covering in our presentation. So, how do nuclear reactors work? A nuclear reactor utilizes the control of chain reactions brought on by the bombardment of uranium 235 via a neutron. This process, as you know, is called nuclear fission. Neutron accepting rods are used to control that chain reaction, usually boron 10. Pressurized water is heated by reactions and that water is relayed. Water is boiled into gas in a second compartment that acts as a coolant, which spins turbines, generating electricity. Here's an overview of that chain reaction that I mentioned. You have one neutron getting shot into a uranium 235 atom isotope. That split releases massive amount of energy in the form of heat and three other neutrons. These then are shot into other uranium 235 atoms, which then go on to release more energy and so on and so forth. Here is that nuclear reactor, or at least the basis of it. Here we have fuel rods, which are loaded with nuclear fuel pellets. Here we have Steve to give you a scope of the size of these fuel rods. These fuel rods are then kept in the core of the reactor. This is where the reaction takes place and where the water is heated, being shot through the coolant loop into the steam generators, thus generating steam to turn turbines and generate electricity. Here we have the control rods, which are lowered and or raised to control the reaction. Here's some general statistics. About 440 nuclear plants are used in operation today worldwide. 96 of those are used in the US, and they've been operating for an average of 38 years. Now, these nuclear reactors were meant to last 40 years before they'd have to be rebuilt or torn down to make new nuclear reactors. However, that costs billions of dollars. So they've been renewed to last 60 more years, and that's where these reactors start to fall into some problems. Corrosion in nuclear reactors, specifically stress corrosion cracking, or SCC. These reactors were designed for a lifespan of 40 years, now expected to last 60 more years. The metal lining inside the chambers have begun to corrode. The constant heat, pressure, and transfer of radioactive material has caused the welding to weaken and crack. Another issue that these reactors have is the material that the fuel rods are made of. You see, when zirconium oxidizes, it releases a massive amount of energy because that reaction is exothermic. This adds a unpredictable and unnecessary amount of heat to that reaction chamber. So let's talk about SCC. The most common type of reactor are pressurized water reactors, which operate under pressure to allow liquid water to reach 320 Celsius. They also contain radioactive material constantly. This increases the rate of oxidation and causes SCC. This picture here shows SCC in the metal of the nuclear reactors. It will only continue to crack the metals until they finally break apart, which will ultimately result in a leak of radioactive material. In the welding, the alloy used for the welding, which joins the parts of the reactor, is beginning to crack first and experience SCC. The effect that this has can be documented in the David Best reactor incident. In short, the David Best reactor incident was caused by the weakness in the weldings of the reactor. SCC had caused tiny cracks to occur, which disengaged the control rod mechanism. Cracks also allowed hot borated water to slowly escape the interior of the reactor. This event also caused a football-sized hole in the reactor head, according to Bogdan Alexandru of Argonne National Laboratories, an expert in corrosion who analyzed pieces of the damaged head. This event could have completely ruined the reactor altogether. The alloy used to build this reactor was to blame for this situation. So let's talk about alloys then. Inconel alloy 600 and 690. Both are composed of chromium, nickel, and iron. However, they vary in the concentration of elements, particularly chromium. When chromium metal interacts with oxygen in the air, it forms a chromium oxide layer. This layer protects the rest of the alloy underneath it from the oxygen, thus preventing oxidation. Now, when that metal gets kinked or the chromium oxide layer is damaged, it can then repair itself and reform that layer. The more chromium you have in your alloy, the better it is at doing this. Therefore, Inconel alloy 690 was preferred over 600. As for the welding of the nuclear reactor, Inconel alloy 152 and 182 are called into question. Now, 152 is 30% chromium by weight, and 182 is 16% chromium by weight. They're making 152 the better alloy decision. As for Inconel alloy 600 and 690, 600 is composed of 15% chromium by weight, while 690 is 28%. Here we can see how much of a difference that really makes. Inconel alloy 690 sees much less decrease in weight change compared to Inconel alloy 600 under cyclic heating and cooling over the course of 1,000 hours. Here we can see that 600 does not hold up as well as alloy 690. That chromium by weight difference in Inconel alloy 690 made it much more resistant to the extreme temperature changes much seen in a nuclear reactor. Preferring an Inconel alloy with a higher chromium concentration is one of the major ways that nuclear reactors can prevent stress corrosion cracking. That oxide layer makes all the difference, and the better it can withstand those high pressures and high heats of the nuclear reactor.
Because of zirconium's reactivity in light water reactors, many researchers sought to replace or enhance the materials with other alloys and chemicals. One of these attempts at accident-tolerant fields can be seen in General Electric's ironclad alloy, composing of iron, chromium, aluminum, and molybdenum. This alloy is able to endure steam and hot water reacting. At the moment, General Electric is still assessing on whether the material should have a 12 or 21% of chromium for light water reactors. Another attempt at ATFs can be seen in the armor coating, which can be applied to a normal zirconium cladding, allowing it to take on 1,000 degrees Celsius without any sign of corrosion or oxidation. For creating a controlled fission, a zirconium alloy is used for storing uranium pellets as a cladding. The metal is ideal for this due to being permeable to neutrons needed for the reaction. In a loss of coolant accident, hot steam caused by leaks in the coolant system oxidizes the zirconium cladding, which produces flammable hydrogen gas as well as a lot of heat, which can overwhelm the reactor. An example of this can be seen in the inability of the Daiichi Fukushima power station during the 2011 earthquake, as its inability to control the flow of water due to damages in the coolant system ultimately lead to a series of hydrogen gas explosions. Molten salt reactors stands out when compared to light water reactors because instead of using water as a coolant like LWRs, MSRs use molten salt to cool down the fuel. Moreover, it is used to contain the fuel while being permeable towards neutron particles, meaning that you don't have to worry about a loss of coolant accident and subsequent hydrogen gas accumulation in LWRs. MSRs don't have to worry about overheating, making it more efficient and can work at atmospheric pressure, while LWRs need a safety system and tough alloys since it cannot operate under these conditions.
Thank you for listening to our presentation. If you have any questions, please ask them. The article listed below is a major resource for this presentation, and any images or videos shown are not mine.